Good morning, students. Today's topic, Unit 3, Multivariable Calculus. In that, the topic is Jacobian. Contents, Introduction about Jacobian, Jacobian definition, properties of Jacobian, functional dependence and independence, and applications, that is problems. Introduction, Carl Gustav Jacob Jacobi was a German mathematician who made fundamental contribution to elliptic functions, dynamics, differential equations, determinants, and number theory. Jacobi was the first Jewish mathematician to be appointed professor at German University. Jacobi carried out important research in partial differential equations of the first order and applied them to the differential equations of dynamics. He also worked on determinants and studied the functional determinant now called the Jacobian. Jacobi and Euler were kindred spirits in the way created their mathematics. Both were prolific writers and even more prolific calculators. Both drew a great deal of insight from immense algorithmical work. Both labored in many fields of mathematics. He is Carl Gustav Jacob Jacobi. Definition: if u and v are functions of two independent variables x and y. So here u and v are two functions with respect to x and y. Then the determinant of dou u by dou x, dou u by dou y, dou v by dou x, dou v by dou y. This determinant is called Jacobian or Jacobi and is denoted with dou of uv by xy or j of u comma v by x comma y. So it is the determinant. It is called as a Jacobi or Jacobian of uv with respect to x and y, where uv's are functions in terms of x and y. Similarly, uvw are functions in terms of xyz. Then the Jacobian of uvw with respect to xyz is given by j of uvw by xyz is dou of uvw by dou of xyz is determinant of ux, uy, uz, vx, vy, vz, wx, wy, wz. These are the partial derivatives with respect to xyz, the partial derivatives of u, v, w. This can also be written as dou of uvw by dou of xyz is a determinant of dou u by dou x, dou u by dou y, dou u by dou z, dou v by dou x, dou v by dou y, dou v by dou z, dou w by dou x, dou w by dou y, and dou w by dou z. So this is called Jacobians of uvw with respect to xyz. Applications of Jacobians. If u is x cos y, v is y sin x, then find dou of uv by dou of xy. The formula for dou of uv by dou of xy is a determinant dou u by dou x, dou u by dou y, dou v by dou x, dou v by dou y. To compute this Jacobian, we need these partial derivatives. Partial derivatives of u with respect to x. While differentiating partially with respect to x, keep y as constant. Cos y constant, x derivative 1. Dou u by dou y, differentiating u partially with respect to y. Keep x as constant. X constant, cos y derivative minus sin y. Dou v by dou x, differentiating v partially with respect to x, keeping y as constant. So y keep it as a silent, sin x derivative is cos x. Dou v upon dou y, differentiating v partially with respect to y, keeping x as a silent, sin x keep it as a silent, y derivative is 1. These are the partial derivatives of UVs with respect to x and y. Now we have to compute the determinant. So we know that the determinant of ABCD is AD minus BC. Like that, cos x into sin x into cos y, sorry, cos y into sin x is sin x cos y, minus into minus plus AD minus BC. X sin y into y cos x, that is xy cos x sin y. So it is the value of dou of uv by dou of xy. It is the Jacobian of uv with respect to x and y. Application: if u is yz by x, v is zx by y, w is xy by z, then show that dou of uvw by dou of xyz is 4. By data uvw, dou of uvw by dou of xyz formula, determinant formula. Now we have to substitute all the partial derivatives of uvw with respect to xyz. These are the partial derivatives. Don't forget, while differentiating partially with respect to x, keep yz variables treated as constant. While differentiating partially with respect to vy, keep xz as constant. While differentiating w with respect to z, keep xy as constant. So these partial derivatives are computed same as above. Now we have to compute the determinant for 3 by 3 matrix. On simplifying, we will get like this. That is, on simplifying, all terms are here, get cancelled like this. 0 plus 1 plus 1 plus 1 is 4. So it is the required value of dou of uvw by dou of xyz. Another example: if x plus y plus z is u, y plus z is uv, z is uvw, then evaluate dou of xyz by dou of uvw. To evaluate this, xyz must and should be in terms of uvw. So to get these dou of xyz by dou of uvw, the xyz must and should be in terms of uvw. For this, we have to convert xyz in terms of uvw using the given equations. So given equations, but third equation, that is z is uvw, already z in terms of uvw. Now, second equation, that is y plus z is uv. Thus, we will have y is uv minus z. But what is z here? Uvw. So, replacing z as uvw and taking out uv, we will have y is uv into 1 minus w. Thus, y becomes in terms of uvw. Similarly, x from first equation we will have x is u minus of y plus z. But what is the value of y plus z? Y plus z value is uv. Substituting, we will have x is u minus uv. Now taking out u as common, that is u into 1 minus v. Thus, all three xyz are clearly in terms of uvw. Now we can evaluate the required Jacobi, that is a dou of xyz by dou of uvw is the determinant xu, xv, xw, yu, yv, yw, zu, zv, zw. So computing this determinant, xu means partial derivative of x with respect to u. While differentiating partially with respect to u, keeping v as a constant and w as constant, that is 1 minus v is treated as constant, u derivative is 1, that is 1 minus v. Another partial derivatives are also computed same as like this. Another example, zw. Zw means dou z by dou w. That is partially differentiating z with respect to w, keeping x u v as silent. That is uv constant, w derivative is 1. So thus we will have uv. It is the value of zw. Similarly, other partial derivatives are also easily computed. Now, using row operation, we can simplify this determinant easily. For this, making the row operation, that is R2 goes to R2 plus R3. Just adding second row and third row. so that this element clearly becomes 0. Negative uv plus positive uv is 0. Similarly, other two elements can also be added with third row elements. The determinant is becomes like this. Now we can evaluate the determinant for third column. So computing the third column determinant, because we are evaluating the third column determinant, since we are having two zeros in third column, so that we can evaluate the determinant easily. So evaluating the determinant, deleting the row and column which contains uv. Now we will have the submatrix 1 minus v minus u v u, whose determinant is uv into 1 minus v into u, that is u minus uv. AD minus BC, formula having minus. Now the product minus U into V minus UV, product having minus, but minus into minus plus, that is plus UV. So it is the determinant value. Clearly here negative UV and positive UV get cancelled. U into UV is U square V. So it is the required Jacobian value of XYZ with respect to UVW. Another example, if uv is x square minus y square, v is 2xy, where x is r cos theta, y is r sin theta, then show that dou of uv by dou of r theta is 4r cube. Now to evaluate this Jacobian, UV's must and should be in terms of r theta. But here given that UV's are in terms of xy. But using these equations, x is r cos theta and y is r sin theta, we can reduce UV's in terms of r theta. Substituting, uv is x square minus y square, r cos theta whole square is r square cos square theta minus r sin theta whole square is r square sin square theta. Now taking out r square, we will have r square into cos square theta minus sin square theta. But cos square theta minus sin square theta is cos 2 theta. V is 2xy, but x is r cos theta and y is r sin theta. That is a 2 r cos theta into r sin theta, 2 r square cos theta sin theta. Now taking out r square, 2 cos theta sin theta is sin 2 theta. Thus clearly UVs are now in terms of r theta. Now we can evaluate dou of UV by dou of r theta, that is the Jacobians of uv with respect to r theta. It is the determinant value, determinant of ur u theta, vr v theta. Ur means dou u by dou r, u theta means dou u by dou theta, vr means dou v by dou r, v theta means dou v by dou theta. Now evaluating the partial derivatives of uv with respect to r theta. Substituting all these values and then simplifying, we will get the determinant value is 4r cube. Clearly here cos square 2 theta plus sin square 2 theta is 1. Cos square theta plus sin square theta value is 1. Here cos square 2 theta plus sin square 2 theta value is also 1. Determinant for submatrix, r cos 2 theta into cos 2 theta is r cos square 2 theta. AD minus BC, that is minus r sin 2 theta into sin 2 theta is minus r sin square 2 theta. But the formula having minus, AD minus BC. So minus into minus plus. So thus we will have r cos square 2 theta plus r sin square 2 theta. Taking r as common, already we have 4r square. 4r square into r is 4r cube. But cos square 2 theta plus sin square 2 theta value is 1. So it is the required value of dou of uv by dou of r theta. So once again, to evaluate dou of uv by dou of r theta, uv's must and should be in terms of r theta. For this, we have to reduce UVs in terms of r theta by using the equations x is r cos theta and y is r sin theta. Just replacing xy values, now clearly UV becomes in terms of r theta. Now we can evaluate the Jacobians clearly. So thus we will have the Jacobians value is dou of uv by dou of r theta is 4r cube. Hence proved. Another important sum, if x is r sin theta cos phi, y is r sin theta sin phi, and z is r cos theta, then show that dou of xyz by dou of r theta phi is r square sin theta. These are the equations which are nothing but spherical polar coordinates whose Jacobian value with respect to r theta phi is r square sin theta. So to evaluate this, the required xyz must and should be in terms of r theta phi, clearly given equations like this. Now we can evaluate easily the determinant dou of uxyz by dou of r theta phi. The Jacobian's value easily evaluated. For this we require the partial derivatives, that is dou x by dou r, dou x by dou theta, dou x by dou phi, dou y by dou r, dou y by dou theta, dou y by dou phi, dou z by dou r, dou z by dou theta, and dou z by dou phi. So first of all, if the differentiating x partially with respect to r, keeping theta phi as constant. Sin theta cos phi is constant, r derivative is 1. Similarly, other partial derivatives are also evaluated. For example, dou z by dou theta. While differentiating z partially with respect to theta, keep r as a constant. R constant, cos theta derivative is minus sin theta. Phi is also treated as constant. So, but dou z by dou theta is r constant here, cos theta derivative is minus sin theta. Like these, all partial derivatives are easily evaluated. Just we have to know about the partial derivatives with respect to r is 1. Sin theta derivative with respect to theta is cos theta derivative with respect to theta is minus sin theta. Sin phi derivative with respect to phi is cos phi derivative with respect to phi is minus sin phi. So evaluating all these partial derivatives and now using the formula, that is a dou of xyz by dou of r theta phi, the formula, substituting all the above values. Now taking common as, just to take the common as r in second column, and in third column we will have r square, and taking common sin theta in third column. So thus we will have r square sin theta as the common, and then evaluating this determinant and then simplifying, we will get like this. So we have to know about sin square theta plus cos square theta is 1, and sin square phi plus cos square phi is 1. So just simplifying, we will get r square sin theta is the required Jacobians of xyz r theta phi with respect to r theta phi. Don't forget the Jacobi quotient value is important one. Here the using the equations are spherical polar coordinates. To change these Cartesian coordinates into spherical coordinate in multiple integrals, we have to use the Jacobian value. So here Jacobian value is r square sin theta for spherical polar coordinates. Properties of Jacobians. Property: if J is Jacobian of UV with respect to xy, and J dash is the Jacobian of xy with respect to UV, then JJ dash, that is a dou of UV by dou of xy into dou of xy by dou of UV is 1. The product of two Jacobians is equal to 1. This is called inverse property of Jacobians. If we know the J value, we can compute J dash value. Suppose J is 5, then J dash will be 1 by 5. Suppose J is r square sin theta, then J dash will be 1 by r square sin theta. So it is known as inverse property. Another property, if UV is U and V are functions with respect to R and S, and RS are in terms of X and Y, then J is dou of UV by dou of XY is equal to dou of UV by dou of RS into dou of RS by dou of XY. This is called the chain rule of the Jacobians. So once again, UVs are in terms of RS, but RS are in terms of XY. Then whose product will be dou of UV by dou of XY. This property is known as chain rule. Another problem. If x plus y square is u, y plus z square is v, z plus x square is w, then find dou of xyz by dou of uvw. Now to evaluate this Jacobian xyz must and should be in terms of uvw. But in the problem given equations are uvw's are in terms of xyz. For this, first we evaluate dou of uvw by dou of xyz. The formula is determinant of ux, uy, uz, vx, vy, vz, wx, wy, wz. Ux means dou u by dou x, differentiating u partially with respect to x, keeping yz as constant. X derivative 1, y square derivative 0. Dou u by dou x value, that is ux value, is 1. Similarly, other partial derivatives are also calculated. Thus, we will have dou of uvw by dou of xyz is 1 plus 8 xyz. Now, using the first property, that is inverse property, we will have dou of xyz by dou of uvw is 1 upon dou of uvw by dou of xyz. But what is the value of dou of uvw by dou of xyz is 1 plus 8 xyz. So thus we will have dou of xyz by dou of uvw value is 1 by 8x plus y plus z. Dependence and independence. Functional dependence. Two functions u of xy, v of xy are said to be functionally dependent on one another if the Jacobians of uv with respect to xy is 0. If they are functionally dependent on one another, then it is possible to find the relation between these two functions. So once again, the Jacobian value is 0, then UVs are called functionally dependent. And also there exists a unique relation between UVs. If the Jacobian value is not equal to 0, then UVs are called functionally independent. Problem: prove that the functions UVW are functionally dependent and find the relation between them. Given UVWs, dou u by dou x, differentiating u partially with respect to x, keeping yz as constant, yx derivative is y, zy derivative is z. Computing other partial derivatives also, and computing the Jacobian value dou of uvw by dou of xyz, it is the determinant of dou u by dou x, dou u by dou y, dou u by dou z, dou v by dou x, dou v by dou y, dou v by dou z, dou w by dou x, dou w by dou y, dou w by dou z. Now computing the partial derivatives and substituting in the determinant, and then simplifying the determinant by using row operation, that is r1 goes to r1 plus r2, just adding the first two rows. So we will have a common term, that is x plus y plus z in first row. Now taking the common as x plus y plus z, so we will have the two rows are identical, that is r1 and r3 are identical. So small mistake is there, r1 and r3 are identical, so that the determinant value is 0. Thus, we will have the functionally UVW are functionally dependent. Also, there exists a functional relation between U, V, and W. For this, consider W. W is x plus y plus z. Now, squaring on both sides. So, we will have W square is x plus y plus z whole square. Now, expanding x plus y plus z whole square, that is x plus y plus z whole square expansion is x square plus y square plus z square plus 2xy plus 2yz plus 2zx. Now taking 2 as common, that is 2 into xy plus yz plus zx. But substituting the given values, that is uv is xy plus yz plus zx and v is x square plus y square plus z square. So we will have a unique relation between UVW, that is W square is 2U plus V. It is the relation between U, V and W. Another problem, show that the functions UVW are functionally related. Functionally related means we have to show that the Jacobian value is equal to 0. Computing the partial derivatives which are required in dou of UVW by dou of xyz whose determinant. So the partial derivatives are computed, so substituted, and then simplifying. So to simplify, we have to take out the common. That is, 2 is taken out the common in second row, and 3 will be taken out the common in third row. That is, 2 into 3 is 6, and simplifying the determinant. So we will have the two columns are identical here, that is of C1 and C2 are identical. C1, C2, C3 are denotes the columns, R1, R2, R3 are denotes the rows. So clearly the two columns are identical. We know that the property of determinant, that is if any two rows or two columns are identical, then whose determinant value is 0. So clearly the determinant value is 0 here. That is a dou of UVW by dou of XYZ is 0. Whenever the Jacobian value is 0, then the functions UVW in that Jacobian are called functionally dependent. Whenever the functions are functionally dependent, then there exists a functional relation also. So clearly proved there exists a functional relation. Another example, prove that XYZ are functionally dependents? Question mark. So clearly Jacobian value is a 4 here. So 4 means not equal to 0. Clearly functionally independent. Just we have to compute the Jacobian value with respect to UVW. Jacobians of XYZ with respect to UVW. All derivatives are substituted here. Now we have to simplify the determinant. On simplifying, we will get the 4 as result. Since the Jacobian is non-zero, XYZ are functionally independent. Another problem, verify UV is 2x minus y plus 3z, V is 2x minus y minus z, W is 2x minus y plus z are functionally dependent. If so, find the relation given UVW values. Dou of UVW by dou of XYZ. The formula is a determinant of dou u by dou x, dou u by dou y, dou u by dou z, dou v by dou x, dou v by dou y, dou v by dou z, dou w by dou x, dou w by dou y, dou w by dou z. Computing the partial derivatives of u with respect to x, y, z. For example, u with respect to x derivative, that is dou u by dou x is 2. Minus y derivative 0, 3z derivative 0. Another example, dou w by dou x, 2x derivative 2, negative y derivative 0, z derivative 0, that is 2. So it is the value of the determinant of 2 minus 1 3, 2 minus 1 minus 1, 2 minus 1 1. Now we have to evaluate this 3 by 3 matrix determinant. So for this we have to just take out the common as a minus 1 and then simplifying. So clearly here two columns C1 and C2 are identical. When any two columns or two rows are identical, then whose determinant value is 0. So that is 2 into minus 1 into 0 is 0. Thus UVW are functionally dependent. Whenever the two functions or three functions are functionally dependent, then there exists a unique relation. So the relation, for this relation, consider u plus v minus 2w. Just adding u plus v and subtracting from 2 into w. So like this. So on simplifying, we will have 0 because all terms are here get cancelled. So thus we will have a relation that is a unique relation. The relation is unique relation means only one relation is existed in between u, v, w. The relation is u plus v minus 2w is equal to 0. Another problem, u is x plus y by 1 minus xy, v is tan inverse x plus tan inverse y. Find dou of uv by dou of xy. Hence prove that uv are functionally dependent. If so, find the relation. Given u is x plus y by 1 minus xy and v is tan inverse x plus tan inverse y. To compute the Jacobian value, first we have to find out the derivatives, partial derivatives of u's with respect to x and y. Now dou u by dou x. Dou u by dou x is obtained by differentiating partially with respect to x using u by v formula. So what is u by v formula? Vu dash minus vu dash whole by v square. So 1 minus xy kept silent, x plus y derivative is 1 minus x plus y kept silent, 1 minus xy derivative. 1 derivative 0 minus xy derivative is minus y because we are evaluating the partial derivative of u with respect to x, keeping y as constant. So whole by v square. V square means 1 minus xy whole square. Now on simplifying, 1 into 1 minus xy is 1 minus xy, minus y into minus is a plus, plus y into x plus y is xy plus y square, negative xy, positive xy get cancelled, 1 plus y square by 1 minus xy whole square. It is the value of dou u by dou x. Similarly, dou u by dou y can be obtained by using the partial derivative of u with respect to y, keeping x as constant. So on simplifying, we will get 1 plus x square by 1 minus xy whole square. These are the partial derivatives of u with respect to x and with respect to y. Now since v is a tan inverse x plus tan inverse y, now dou v by dou x means tan inverse x derivative is 1 by 1 plus x square. Tan inverse y derivative 0. Similarly, dou v by dou y is tan inverse x derivative 0. Tan inverse y derivative is 1 by 1 plus y square. So these are the values of dou v by dou x and dou v by dou y. Just we have to know about the formula, that is a derivative of tan inverse x is 1 by 1 plus x square. Now substituting all these partial derivatives in the Jacobians, that is the Jacobians of uv with respect to xy. Determinant, substituting all the above values and computing the determinant, it is look like ABCD. The determinant of ABCD is AD minus BC. So computing the determinant by cross multiplication, we will have 1 plus y square, 1 plus y square get cancelled. Here 1 plus x square, 1 plus x square get cancelled. So we will have the result is 1 by 1 minus xy whole square minus 1 by 1 plus xy whole square. Both are get cancelled, we will have 0. So it is the value of dou of uv by dou of xy which is equal to 0. The Jacobians is equal to 0. That means uv's are must and should be functionally dependent. Whenever the two functions are functionally dependent, there exists a functional relation. The functional relationship is V is a tan inverse x plus tan inverse y. This expression can be written as a tan inverse of x plus y by 1 minus xy. But what is x plus y by 1 minus xy? It is nothing but u. So thus we will have V is a tan inverse u. It is the relationship between u and v. The relation is V is a tan inverse u, or this can also be written as u equal to tan v is the relationship between u and v. Don't forget, functional dependence means Jacobian's value is 0. Whenever the functions are functionally dependent, then there exists a unique q relation, one relation between uv's. These problems are to be work. It is work for you. Do these problems. These are the answers. These are the relationship between UVWs. So to prove these problems, just we have to show Jacobians is equal to 0. Thank you. For any queries, doubts or clarifications, please contact. And this is my mail address. You can mail also. Thank you.